Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to look at why do we use two corrections and why do we use Z in the adaptive techniques. So in this topic, we will discuss why we use two corrections, specifically estimating the error of Y using twice the difference between Z and Y, and why we use 0.9 times A times H as the next step size as we iterate. We'll also discuss why we use Z when the error estimates are for the approximation Y. To begin, you'll recall that for both adaptive Euler-Hoyne and the adaptive Dorman-Prince methods, there were two corrections we made. First, we claimed that because the error of the poorer approximation was order h to the n, say order h squared for the Euler-Hoyne and order h to the 5 for the Dorman-Prince method, versus the error of our approximation z, which was order h cubed for the Euler-Hoyne and order h to the 6th for Dorman-Prince, we could then estimate the error of y from the true solution by simply calculating the absolute value of z minus y. Now, because z is only an approximation, although be it a better approximation of the actual value, it's still only an approximation. So to ensure that we do not underestimate the error of y, we double this estimate. So we use twice the absolute value of z minus y. Second, once we calculate the new scaling factor A times H, instead of using A times H, we use 0.9 times A times H as the new scaling factor. This is our second correction. Why is this second correction necessary? After all, we're already overestimating the error of y. So why do we now have to use a smaller step size than we normally would need to? Now recall why we calculate A. We're calculating the scaling factor A because we're looking for the ideal step size that ensures that the error with the next calculation will be epsilon abs times H. That is the maximum error per unit time times the width of the interval. The issue is, in calculating A, we are already using the first overestimate of the error of y. Additionally, this approximation is not going to be perfect because, after all, we are only approximating the error of y. Additionally, we also truncated the Taylor series to get our estimate. All right, so suppose that we approximate the next value with a given step size h and we calculate the scaling factor a. We find that a is equal to 0.831, which is less than 1. What this means is that we have to recalculate the approximation of the next value, but this time we must use a smaller step size, specifically 0.831 times h. Now, problem. Assuming that this is close to the ideal step size once we've recalculated the value of the step size, with the next recalculation, we're going to calculate a new value of a, and a should be approximately equal to 1. The problem is, if a is going to be approximately equal to 1 with the next recalculation, then there's essentially a 50-50 chance that a will once again be less than 1. Thus, half the time, we will have to recalculate this step once again. The worst case scenario is that we continue to have to recalculate the current steps, but the scaling factors we get are well, first 0.831, then 0.9175, then 0.9938, and so on and so forth. This could be a significant amount of work. We may never get to a value of a that is greater than 1 simply because of the characteristic of the differential equation that is being approximated. So we may never actually get to the next step. Similarly, suppose we approximate the next value with a given step size h, and we calculate the scaling factor a, and we find that a is 1.238, which is greater than 1. Well, that means that the current approximation is good enough, and so we're going to proceed to the next step, but with this next step we will use a larger step size, specifically 1.238 times h. Problem. Again, assuming that this is close to the ideal step size, it follows that we calculate the new scaling factor a for the next step, we will once again have a very close to 1. Problem. As before, if a is close to 1, then for the next step, there's essentially a 50-50 chance that a will, for that next step, once again be calculated as being less than 1. Thus, even if a is greater than 1 for the current step, 50% of the time, for the next step, we will once again have to recalculate it. So this is going to give us a lot of extra work. Thus, instead, by using 0.9 times a times h as the next step size, what that means is that with the next step, when we calculate the scaling factor a, it's very likely to be closer to 0.9 reciprocated, or approximately 1.111. Basically, this ensures that with the next step, a will always be probably greater than 1. So this ensures that while our step size is smaller than necessary, which is unfortunate, it also ensures that we will not have to recalculate very often. The consequence is as follows. If we use this approach, then we will have to, on average, calculate 11% more steps than is absolutely necessary, but it also means that very seldom will we actually have to recalculate any one step. So that's important here. We want to basically give us a guarantee as to the number of steps that will be required. As an analogy, suppose you're throwing a dart against a painted wall. On the right-hand side, if your dart lands there in the red, you pay $1,000. If, however, your dart appears to the left, you win some money, but the further you are to the left, progressively you win less money. Assume you're the average person, at least with respect to throwing darts. And if not, just make the stripes on the left-hand side narrower. Now, you could aim for the win $980 stripe. However, if you aired to the right, you'd lose $1,000. So in this case, cumulatively, you'd actually lose money. Instead, if you aimed at the win $900 stripe, if you aired slightly to the right, you'd still win money, but you'll always be winning money. This is why we use 0.9 times a times h as the next step size. All right, the next question is why z? You'll recall that with the adaptive techniques we had two estimations of the next value, y and then z. Y was the one that was less accurate, z was more accurate. So the step size that was chosen to ensure that the error of the approximation of y is no greater than epsilon abs times the step size. Question: if we are creating an upper bound for the error of y, why are we using z as the approximation for the next value? Answer: unfortunately, it's subtle. Generally, z will be more accurate than y anyway. So since we've calculated z, we might as well use it. In fact, Dorman Prince chooses the coefficients for y and z to minimize the coefficients of the error for z. This doesn't happen to actually be the case for another algorithm called Runge-Kutta-Thelberg. Question: if using z usually gives us a better approximation anyway, and in fact it does give a significantly better approximation, why can't we use a larger step size? Answer: well, you could, but you wouldn't have any idea as to how much larger that step size could be. We have no estimate for the error of the more accurate approximation. Consequently, we would have no assurance that the error of our approximation is appropriately constrained. Now, something that's fun, all of the online algorithms that are implemented for you use z. Well, what you can do is have them use y as the approximation, and you'll interestingly find that in fact this does actually work quite well. So if you actually look at the error after a number of intervals, say even one time step, the error is going to be approximately epsilon abs. So it's actually quite nice, and then you can compare that with the result using z. However, important point there is it does actually seem to work quite well as is. Using z seems to be appropriate, at least for Dorman Prince. So following this topic, you understand that the overestimate twice the difference between z minus y ensures that we are overestimating the error of y. You understand that the next calculated scaling factor a ensures that with the next step, it's very likely that a will be approximately equal to 1. And you realize that this means that there will be approximately a 50-50 chance with the next step that we actually will have to recalculate with a smaller step size. Consequently, you know that instead, we reduce the likelihood of having to recalculate to something that's very small, and the additional cost therefore is that we will only have approximately 11% more steps than is actually necessary. Finally, you understand that the error estimate is for y, but we use z as it is more accurate. But we cannot increase the step size because we have no error bounds on the error for z. Here are the references, acknowledgments, the colophon, and a disclaimer. Cheers!